Hello, everyone. My name is Oksana, and I'm a postdoc at the Nordic Institute of Theoretical Physics in Stockholm. And today I'm going to talk about non-Gaussianity in rapid turn multifield inflation. To start with, my talk is about early universe cosmology, and I'm going to zoom into era of inflation, and in particular talk about non-Gaussianity production during inflation. Nowadays, inflation is the leading framework of the early universe physics. It solves horizon and flatness problems and produces seeds for all structure, because inflaton field creates quantum vacuum fluctuations that translate into classical density fluctuations after inflation that become temperature fluctuations in the CMB. So quantum fluctuations during inflation can be characterized by two-point correlation functions in the CMB that is determined by the power spectrum. And power spectrum, in turn, can be characterized by its amplitude, A sub s, and N sub s, that is called the scalar spectral index. And we know quite well both amplitude and scalar spectral index from observations but that were found by several experiments. And here you can see the plot from the Planck experiments that shows standard to scalar ratio and primordial tilt with respect to the primordial tilt. And this data could have already helped us to rule out a bunch of models of inflation. One additional source of information is non-Gaussianity. So essentially, similarly to the two-point correlation function, one can consider three-point correlation function in the CMB that is characterized by the bispectrum. And essentially, the non-Gaussianity of the field perturbations during inflation occurs as a result of some nonlinear evolution of initially Gaussian fluctuations. And the bispectrum can be defined as a sum over all possible shape functions that are determined by function S that depends on particular configuration of the wave numbers K1, K2, and K3 that sums up to 0 altogether. So one can construct different shape triangles using these three wave numbers, and one example is a local shape or equilateral or folded shapes. And the amount of non-Gaussianity of inflationary perturbations is quantified by the parameter that is called FNL, which is defined as the ratio of the bispectrum to the permutation of the power spectrum. And more than 20 years ago, by Maldacena, it was shown that FNL of any shape for single field inflation is proportional to slow-roll parameters, epsilon and eta, that both are much smaller than 1. So generically, from single field inflation, non-Gaussianity is expected to be very, very small. And 10 years after that, by two different groups, it was shown that the local FNL, which is sometimes called as the squeezed limit, where one long wavelength mode couples to the two short wavelength modes. So in this limit, the FNL parameter exactly equals to 0 for single field inflation. It means that if the FNL of order 1 would be detected in the upcoming CMB stage 4 or large-scale structure experiments, it would rule out all attractor models of single field inflation. And current CMB constraint is shown here. And in the next decade, we hope that observational experiment will be able to zoom even more into order 1 non-Gaussianity and hopefully measure this number. So now the question is, if single field inflation cannot produce local non-Gaussianity, and if in case this number will be measured, then probably there is some additional degrees of freedom during inflation. And we arrived at the notion of the multifield inflation. So multifield inflation nowadays is a very active research direction. And one of its interesting features is, for instance, that it doesn't require flat potential anymore to have slow roll inflation, but the potential can be quite steep. That's because the inflationary trajectory doesn't have to be straight in the field space, but it can be bended, as for instance shown in this first plot. Also, it's possible to have some sharp turns in the inflationary trajectory that could produce some additional signatures in the power spectrum of fluctuations. So this is the most general form of the action of multifield inflation, and here GAB is the field space metric and V of phi is the multifield potential. And as I have already mentioned, in multifield, the inflationary trajectory generically is not straight. So one can define the unit vector E parallel that is tangential to inflationary trajectory and another unit vector E perpendicular that is orthogonal to it. And the turn rate, or also bending on the field trajectory, is defined as the rate of change of the unit vector that is tangential to the field trajectory. And because of this, in multifield inflation, there are two types of field perturbations. There are adiabatic or curvature perturbations that are tangential to the inflaton trajectory, and non-adiabatic or isocurvature perturbations that are orthogonal to it. And equation of motion for curvature and isocurvature perturbation is very well known since long time ago. And very interesting point is that this perturbation, they are coupled by the turn rate. So essentially, the curvature perturbation gets sourced by isocurvature, and the sourcing is proportional to the bending parameter. And not only that, it also depends on the potential and on the geometry of the field space that is encoded in the Riemann tensor of the field space. So if one solves the equations of motion for curvature and isocurvature perturbation, one can construct the power spectrum of curvature perturbation, cross correlation, and isocurvature perturbations. And important point to mention that if the turn rate is large, then the cross correlation term typically cannot be neglected anymore because of the large sourcing of curvature perturbation by isocurvature. So in 2011, it was shown that it's very hard to generate large FNL local in multifield inflation in a slow turn approximation. So one can understand that because FNL local in this formula is proportional to tensor to scalar ratio that is observationally constrained to be small. Then it depends on a function of TRS, where TRS is a function that characterizes the sourcing of curvature perturbation by isocurvature. It also depends or proportional to the turn rate, but in any case, this function, this ratio, can never be larger than 1. And the last is that this contribution was shown to be initial condition dependent. So even if it's possible to generate big enough FNL local in multifield inflation with a slow turn, then the underlying model has to be largely initial condition dependent. So generically, it is very hard to generate large FNL in slow turn multifield inflation. Now the question pops up, what is different in the rapid turn regime of multifield inflation? And that's the question that we have asked with my collaborators, David Marsh and Gustavo Salinas from Oscar Klein Center in Stockholm University. And I'm going to tell you about our findings. So in order to compute non-Gaussianity in rapid turn inflation, we used delta N formalism. And I just want to say a couple of words about it. So delta N formalism uses the notion of the curvature perturbation as a scalar perturbation to the spatial part of the metric. And according to the delta N formalism, curvature perturbation can be defined as a change in the number of e-folds between uniform density hypersurface and initial flat hypersurface on the one hand, and on the other hand, the change in the number of e-folds during inflation depends on the field perturbation around horizon crossing. So here we can see the plot of two different inflationary trajectory if one changes slightly initial conditions around horizon crossing. So this leads to the slight change in the number of e-folds that can be related to the curvature perturbation. So we use the delta and formalism to compute the bispectrum. And one can expand it in terms of the number of e-folds and derivatives of the number of e-folds with respect to the fields in the following way. So here you can see the two contributions, two leading contribution to the 3-point functions. And the first contribution, it encodes the horizon crossing contribution to the bispectrum, and the second one encodes the super horizon evolution of it. So if one computes FNL would also depend on these two contributions. And in our work, we focused more on super horizon contribution to the bispectrum. So the main difference between the slow roll and slow turn inflation essentially is the way how to describe the perturbations. So in the slow turn regime, the 2-point correlation function is proportional to the delta function, meaning that the power spectrum of curvature perturbation and isocurvature perturbation can be set equal to each other around horizon crossing, and the cross correlation is identically 0. However, in the rapid turn inflation, it's no longer the case because of the large bending, of the large coupling of curvature and isocurvature perturbation. So one has to consider the 2-point function to be proportional to some matrix PAB that encodes that all of the power spectra are non-zero and non-equal to each other. With this setup, one can compute the formula for FNL using the delta and formulas, and this is the standard result in the slow turn approximation. And one can see that in the rapid turn, the result is slightly complicated, precisely because of the appearance of this matrix PAB that permutes all of the derivatives of the number of e-folds. And if to work out this formula a bit better and write it in different form, one arrived to the following form of the non-Gaussianity parameter in the rapid turn regime. So here you can see that FNL appears to be as a sum of the power spectra of curvature and isocurvature of curvature perturbation and the cross correlation, and the contribution from the isocurvature perturbation drops out from this formula. And we can see essentially that FNL4 has 4 different terms. And it's interesting to mention that FNLRR remains to be local. It doesn't depend on the scale. However, the contribution that are determined by RC, CR, and CC terms here, they generically can have some scale dependence that doesn't cancel from this formula, and also on it can depend on a particular shape of the power spectrum of the cross correlation. So we see that generically in the rapid turn approximation of multi-field, we gain some additional scale dependence and dependence on the new shape functions of the cross correlation. And to simplify this formula slightly more, we can assume the scale invariant power spectrum of perturbation, and then the formula FNL for FNL reduces to the following form, where coefficients I are some time-dependent coefficient that depend on the TRS, on the amplitude of the power spectrum CRS, PS, and PR. And one can see that the first contribution is proportional to the turn rate, and the two other contributions, they proportional to the effective mass matrix. And if the turn rate during inflation is large, then one could expect that the contribution to the non-Gaussianity would also be quite significant. So indeed, we found some new model-independent contributions that can be potentially large and lead to large values of the non-Gaussianity parameter. And to illustrate how our formula works, we considered example angular inflation model that was introduced in 2019. An angular inflation model has two fields, which have a simple quadratic potential, but the field space metric is hyperbolic manifold. So on this plot, you can see the field trajectory during inflation for angular inflation, and on the right plot, you can see the evolution of the turn rate with respect to the number of e-folds, and the value of the turn rate in this model is about 3. So we computed the power spectrum of curvature perturbations, cross-correlation, and isocurvature perturbation using the pi transport code, and found that cross-correlation together with isocurvature perturbation, they decay sometime after horizon crossing, but since the turn rate is significant, it still has some time to source the curvature perturbation and produce some non-Gaussianity. And this is the plot for the non-Gaussianity parameter. This is a numerical plot using the pi transport. And below you can see the formula, our analytical formula for the non-Gaussianity, and putting all the numbers inside, we can find that FNL local is about 0.7, which matches quite well with numerical result. So I came to my conclusions. I just want to sum up that in this work, we extended the delta N formalism to rapid turn inflation. We identified new model independent potentially large contribution to the non-Gaussianity parameter. We found that the resulting bispectrum FNL4 in general could be not of the local shape, but it depends on the power spectrum of the cross-correlation term. And also that the detection of non-Gaussianity of order 1 would signal some new particles, inflation with more than one field, curved field space, steep potentials, and so on, or probably non-inflationary perturbations. Thank you very much. I'm waiting forward to your questions and, of course, to the new data from CNV stage 4 and LSS experiments. Thank you.